at Microsoft for many years and is now at in the Courant Institute at NYU. But before getting to our work, I will give some background on this object, the Ramanujan graphs. Yes? I turned it, but there's... It goes on and off. Yeah, when I switch it, it doesn't. No.
All right.
Okay. Thank you. But I will first present the background on these objects, the Ramanujan graphs, and you'll see some pictures later. But first, so before getting to Ramanujan graphs, we'll talk about the larger class of expander graphs. So these are graphs that can be defined in two equivalent ways. One is in terms of their spectrum. So here, when we look at the graph G, we will look at its adjacency matrix. So we're not normalizing at this stage. So this is just the matrix of zeros and ones, where you have a 1 if the two vertices are connected in the graph. So the adjacency matrix has eigenvalues where the largest one, lambda 1, is just d. So we have a d-regular graph. All the degrees are d. And the one we focus on is the second eigenvalue. And we want the second eigenvalue to be bounded away from d to get an expander family. So it's not really a property of one graph, but we have a sequence of graphs. We say it's an expander family if these eigenvalues are if their supremum along the family is less than d. The first constructions were random. So, for instance, Pinsker showed that if you create a bipartite graph by putting n vertices on the left, n vertices on the right, and taking 3 random permutations, then the union of these permutations gives you a 3 regular bipartite graph, which is an expander with high probability as n tends to infinity. And Bolobash showed that you can do this on just a uniformly chosen d-regular graph. So among all d-regular graphs, you choose one uniformly, and it will be an expander with high probability. And this analysis was refined by Broder and Shamir, and later by Friedman. I'll come to that. So most d-regular graphs are expanders, but that doesn't give you an explicit one. An explicit example was actually constructed by Margulis shortly after Pinsker's work using Kashdan property P. Now there is another point of view on expanders, which is using their expansion. So there is another point and this is the one form of the Chigger inequality proved by Alon Milman and Alon. So we look at this version of the Chigger constant. So it's we minimize over all sets that are less than half the graph. the number of edges from S to its complement divided by the size of S. And then this H of G is bounded above and below, as you see here. The important thing is that if you think now of a sequence of graphs, you see that H of G is bounded below if and only if D minus lambda 2 is bounded below. So we think of a sequence of graphs with a fixed degree D. So D is a constant here. And so this boils down to H of G is between D minus lambda 2 and the square root of D minus lambda 2 up to some constant correction. So along the sequence, an expander sequence forms an expander if and only if H of G is uniformly bounded below along the sequence. So how good an expander can be is determined by this lambda 2, at least from the spectral point of view, and the Alon-Bofana theorem, which is where there is a detailed proof in this paper by Neely. As all of you probably know, Neely is Noga Alon's daughter, who was 2 years old at the time. She's somewhat older now, and the basic inequality is that lambda 2 it has to be at least 2 root d minus 1 up to a correction that goes to 0 as n goes to infinity. It can be more precise, but it's good enough here. So lambda 2 can't stay consistently bounded below from, it can't be less than 2 root d minus 1 minus epsilon if the graph is large. So one significance of this number 2 root d minus 1 is that if you look at the adjacency matrix of the regular tree, so infinite d-regular tree, then this as a, you can think of this as an operator on little l2, and the spectral radius of this operator is exactly twice root d minus 1, and that can yield one of the proofs of the Alon-Bofana theorem is based on this observation. The proof in this Neely paper is more combinatorial. Correct? Anyway, with this in mind, we have this definition of Ramanujan graph. The term was coined by Lubotzky, Phillips, and Sarnak in '88. So this is a d-regular graph that saturates the Alon-Bofana bound. So we want precisely what we want is that all eigenvalues that are not plus or minus d should be in absolute value less than 2 root, or at most 2 root d minus 1. So, so of course d we always have. An eigenvalue of minus d represents that the graph is bipartite. So bipartite graphs are allowed in this definition, but they are a special subcategory. But all other eigenvalues should stay in this interval. We'll see some pictures shortly, but as I said, this definition was coined by both Phillips and Sarnak. They also constructed such graphs explicitly, and another similar construction was given by Margulis. So this construction is based on number theoretic ideas which are related to Ramanujan's work, which is the motivation for this name. But note that the definition doesn't require the graph to arise from number theory. So the ones that they constructed are called LPS graphs, or more generally arithmetic Ramanujan graphs. So they constructed them for d minus 1 is prime. There were other constructions for other values of d, but just a couple of years ago, Marcus Tillman Srivastava showed that there exist bipartite Ramanujan graphs for all d. It's interesting, this proof is, well, it's not constructive and it's not exactly probabilistic. So it certainly doesn't give you an explicit construction, but it also doesn't show that, doesn't give you a natural probability measure where most graphs are Ramanujan. So it doesn't give you a way to pick one at random. It shows that under a very, somewhat strange-looking probability measure, the probability of a graph being Ramanujan is positive, but this positive number is exponentially small. So really all you conclude is that there is one. But so there is a probabilistic element to the proof, but it doesn't give you a way to say. Here are some attempts to draw these graphs. So this is a picture of a small part of the Lubotzky Phillips Sarnak 6 regular Ramanujan graphs. So the vertices are from the group PSL2 over the field of 29 elements, and this is a graph with about 12,000 vertices. The important thing is these graphs tend to have pretty high. So locally they look like a tree. So around this vertex you see locally a tree structure. Of course, this tree structure can't persist forever, and what we'll be interested in understanding the structure over here. It will be less successful to view a small part of the graph. Here is a view of the spectral measure of the graph, but this is actually one picture with two spectral measures on the same slide. So one of them is the dark blue, which is in the foreground, and this is a spectral measure for the LPS graph that you just saw. Now we take the interval, so remember the eigenvalues, there are these plus minus b, we ignore those. All the other eigenvalues are in the interval between plus and minus 2 root d minus 1. We take this interval and normalize it, so this minus 1 and 1 you see here are actually just normalized, so this is, this represents 2 root d minus 1. Okay, and then we take, the height of the histogram represents the multiplicity of the eigenvalue, and just focus on the dark blue for now. So this exactly represents the spectrum of this Lubotzky Phillips Sarnak graph. And you see that eigenvalues come with very high multiplicity. This will be relevant later. So here the multiplicities are at least every one that occurs has multiplicity at least 14. These are the lowest ones here, and some of them have much higher. Okay, so that's one graph. The other graph you see in the background is another Ramanujan graph, which is a random lift of the Peterson graph. So recall this is the Peterson graph, which so a small three regular graph. And the Peterson graph you can explicitly check. This is the characteristic polynomial, so you can see all the eigenvalues here and easily verify that this is Ramanujan. But this is just a small graph. What is the relevance? So there is a construction of random lifts of graphs, analyzed, which is a natural construction, but analyzed a lot by Nati Lineal and his students and co-authors. So given a graph, how do we take this Peterson graph and replicate every vertex 1,000 times? Okay? So now if I look at these, say at these two neighbors, each one now has 1,000 copies. So think of this as a stack of 1,000 nodes and this as a stack of another 1,000 nodes. So we take these two stacks and we put a random matching between them. Okay? So when we do that, now each of these 1,000 vertices will have one on the other side. So all the degree, by this construction, we do this for every edge, pick a random matching. So by this construction, we get a new three regular graph, which is random, but it's still restricted by the fact that we started from the Peterson graph. So one conjecture which is still open is that if you start from a Ramanujan graph, then when you do this with positive probability, which is not going to 1 but going to some positive constant, you'll get a Ramanujan graph from a random lift. We don't know that yet. So, however, when we take this random lift just with 1,000, we get a graph with only 10,000 vertices. So one can check numerically, or to be more precise, my co-author can check numerically that what are the eigenvalues of this graph, and verify that it is indeed Ramanujan. Now, one interesting property that you see here is that if you look at the eigenvalues, so the Alon-Bopana theorem tells you that you must have some eigenvalues here at the very edge, because you cannot have a gap here. But then there is also a related theorem of Serre that says if you look at any fraction, any interval between 2 root d minus 1 and 2 root d minus 1 minus epsilon, that interval, you fix epsilon, that interval must contain a positive fraction of the eigenvalues. So this is true, and one can lower bound it in terms of epsilon. Okay, so these are the spectral measures. So these graphs, the LPS constructions are from the 80s. There are several motivations for renewed interest. One is what I'm talking about now, that we have a much better probabilistic understanding of these graphs. But other connections are, there's a new interest in the diameter of these graphs, and partly because it's been found to be relevant to quantum computing. So this is a story that I don't have time to get into, but in order, when you are trying to build random rotation as a product of basic quantum gates, you get into a problem which is much like navigating in these Ramanujan graphs. There are precise connections that are in this handwritten letter by Sarnak, but it's uploaded on his webpage, so you can read it. Also, one question which we will connect to soon is, what is the diameter of these graphs? So take a Ramanujan graph on n vertices. What is the diameter? And it's certainly at least so the natural thing to compare the diameter is the log to the base d minus 1 of n. It's easy to see that it has to be at least that, because just at that distance you cannot, since the degree is only d, at that distance you cannot accumulate n vertices if you go to a shorter distance. But this is certainly at least 1, and it's known from the late 80s that it's at most 2 plus little o of 1. So there is something on that in the original Lubotzky Phillips Sarnak graph paper on their graphs, and it was generalized by Fan Chang to all Ramanujan graphs. So these are the general bounds we know. This is for any Ramanujan graph. If you take the random d-regular graph, for the random d-regular graph, the left-hand side is inequality. Okay, let me put a little o of 1 here. So then I can say that the left-hand side is inequality for a random d-regular graph. The random d-regular graph, we don't know it's Ramanujan, but it's believed to be such with positive probability. However, this upper bound of 2, we don't know any example where it's attained or even approximated. And in Sarnak's book, which he wrote on this topic, he had conjectured that that in fact the LPS graphs also, the diameter divided by this should be 1 plus little o of 1. But now we know that conjecture is false. So his student Sardari just a couple of months ago uploaded a paper proving that for a certain sequence of these LPS graphs, the diameter is at least 4/3 times log d minus 1n. So d here is p plus 1. So we know a lower bound of 4/3 for an infinite family, and it seems like this 4/3 is the true answer for all LPS graphs. Now there's an interesting combinatorial connection because the bipartite Ramanujan graphs have girth 4/3 log d minus 1n, and these two things seem to be related, but this is still not fully understood. Particularly on the sequence there is this lower bound, but there's no upper bound better than 2 for this ratio. So that's one tantalizing question. Turns out that if we insist on the distances between all vertices, which is the diameter, so diameter is after all the distance between the two largest, but if we just are willing to capture most vertices, then we know the answer, and it is the one on the left. I'll come back to this point. Okay, so how do I turn this off? Maybe like this. Okay. So now I come to kind of our topic, which is the mixing time. So, but it will connect to the distances soon. So, so in order to analyze the random walk, we will measure distance to convergence stationarity using total variation distance. So the total variation distance between two measures is just the maximum difference of mu a minus mu a. We will apply it when mu and nu are both probability measures. So then I could put absolute value here or not, you get the same answer. And this is just half the L1 norm. So if you just take all the vertices and add mu x minus mu x, you'll get the same thing. And so the total variation distance at time t is the maximum over the starting point of the distance between the distribution at time t. So this is the measure you get by starting at x and running for t steps. And the stationary distribution, which in this case is just uniform. So pi is just the uniform distribution over the vertices. So we measure this total variation distance. And the mixing time has a parameter epsilon, which is the first time where the total variation distance goes below epsilon. By the way, this function dTv of t is monotone decreasing in t. So the first time it goes below epsilon, it will then stay below epsilon. And okay, and then there is the question, what is the profile of distances? So I don't think we need the light, I'll just draw. So the distance, the total variation distance to stationarity, once it goes below 1/2, it has to decay at least exponentially. However, in some cases, it decays much faster. And in some cases, there is a very sharp decay in a small interval. And this is the case of cutoff. So T mix of epsilon is the time this graph goes below epsilon. And if you chart two values of epsilon, any two values between 0 and 1, then you see in such a graph, T mix of epsilon and T mix of epsilon prime are very close. So what this means, what this little o of 1 means, it's not as epsilon and epsilon prime are fixed here. And we have a sequence of chains or a sequence of graphs. And we look at the ratio of T mix epsilon and T mix epsilon prime when along the sequence. And along the sequence, the ratio should go to 1. So that's this cutoff phenomenon. Okay. Now the classical examples of cutoff are random transpositions and the hypercube. So this is different from the graphs we're looking at, but these were the first examples of cutoff. So first, what is random transpositions? We have n. So this is a chain on the symmetric group. Think of n cards. You choose one card with your left hand, one card with your right hand. It might be the same one. And you transpose them. Okay. Card and transpose. How long till this mixes? Well, the answer is written there. N log n over 2. Up to 1 plus little o of 1. So as a lower bound, this is obvious just from coupon collector. Each time you're touching only two cards, after all, a random permutation has in expectation just one fixed point. So we had better remove almost all the fixed points before we can mix. So if you look at the set, which is having more than 5 fixed points, this is a set that has small probability for a random permutation, a uniform random permutation. So the set, in order to mix, this set has to have also quite small probability for our chain. So this easily gives you the lower bound of n log n over 2. You have to be able to touch all cards or almost all the cards. The upper bound is much less trivial, and this was proved by Diaconis Shashahani in 81 using some representation theory of the symmetric group. A simpler example, proved by Aldous shortly after, is just the hypercube. So you have n bits, or think of the n-dimensional hypercube, and you do a lazy walk. So each time with probability half you stay in place, probability half you move to one of the neighbors, and there the cutoff is also n log n over 2, which means you don't actually have to move along all coordinates if you moved along all coordinates except for small proportion less than root n. Anyway, these examples, I'm not going to go into more detail. An example without cutoff is a random walk on a cycle. So take a cycle of n nodes, and you do a random walk, and let's make it lazy, so with probability half it stays in place, with probability half it moves to one of the neighbors. This will mix in time n squared, but there is dependence on epsilon. So if you want to get epsilon close, you have to multiply that n squared by a log 1 over epsilon. And this is connected to a spectral feature of this chain. So if you look at the spectral gap for the cycle, it's of order 1 over n squared. Mixing time is of order n squared. So the product of these things stays bounded as we go along the chain. And whenever that happens, the chain cannot have cutoff. So philosophically, cutoff is due to a lot of eigenfunctions participating in the mixing. If kind of one or very few eigenfunctions govern the mixing, then there is no cutoff. And so another very simple example without cutoff is you have two expanders or two cliques, and you connect them with a single edge. Then again, that's example without cutoff. So our intuition is that cutoff is a phenomenon of high dimensions, but high dimensions should be in a certain spectral embedding. So this is intuition. We don't have theorems that have caught up with this intuition, but we're working on it. One thing. So the Serre theorem I mentioned before tells you that in a Ramanujan graph, the highest eigenvalue cannot sit alone. It's surrounded by many close competitors. And this is what is behind cutoff there. However, so people working in this area have known this intuition for decades. So, but we were not able, and believe me, we tried to prove cutoff using this intuition, and we never could. And why not? The reason is that what is the classical recipe to prove cutoff that was used by Diaconis Shashahani and Aldous in these examples? And the many Diaconis and co-authors had a number of examples of cutoff, and often the way this was proved was so the lower bound is often easy by just exhibiting some test statistic that you measure. The upper bound was done by computing L2 norm instead of L1 norm. So remember, the definition of mixing involves this L1 norm, which is the correct way to measure the distance here. But the problem is L1 is a little hard to handle using eigenvalues. So the classical recipe was to use L2, use Cauchy-Schwarz, which bounds L1 via L2. And if this bound matches the easy lower bound, we are done. So and then the L2 calculations you can do spectrally, and then you can find the spectrum using representations and so on. This was the classical recipe. There's still work to carry out the recipe, but this recipe is doomed in the case of bounded degree. So in the case of bounded degree, I'll come to it, but you cannot match this lower bound. The lower bound is, there is an easy lower bound, and the lower bound cannot be matched by the L2 upper bound. I'll come back to that point. Okay, so some more information on simple random walk on these deregular graphs, in particular expanders. So Friedman in 2008 proved the conjecture of Noga-Alon from around 1990 that almost every random deregular graph is weakly Ramanujan, which means lambda 2 is 2 root d minus 1 up to a small error. So it was recently, the original proof was very long. It's now been significantly simplified by Charles Bourdinage. But this error is still too large to conclude that what is believed is that, in fact, lambda 2 is less than 2 root d minus 1 with positive probability. Lubotzky and Sly in 2010 proved, not via spectral proof, but a probabilistic argument, that these graphs have the random deregular graphs have cutoff. This was conjectured by Duret in 2008. They also constructed examples of deregular expanders without cutoff. So these are not Cayley graphs. So by asymmetric, I just mean very far from Cayley graphs. One conjecture I made in an AIM workshop in 2004 is that all transitive expander sequences, so if you have a sequence of graphs, they are Cayley graphs or transitive. So transitive just means the graph looks the same for every vertex. For any two vertices, you have a graph automorphism mapping one to another. So these graphs, any such sequence should have cutoff. At the time, of course, we didn't have any counterexamples. We still don't. But we also didn't have any examples. So there was no single example of a transitive expander sequence where we could prove cutoff. Of course, the LPS was a natural suspect, but Goran last year proposed that maybe just Ramanujan will be enough. So one wouldn't need to analyze the LPS sequence with the arithmetic structure, but just Ramanujan will be enough. And this is what we showed. So if you look at this sequence d over d minus 2 times log d minus 1n, I'll explain where these numbers come from, then you have cutoff, so t mix epsilon minus t star of n is of lower order. So t mix of epsilon does depend on epsilon, but the dependence is of lower order than the mixing time. So this indeed implies that if you take t mix epsilon divided by t star n, this will of course go to 1, and hence it implies cutoff with the definition I showed you before. This root log n is sharp for this problem. Now let me explain where this number comes from. So it comes from random walk on a deregular tree. See, we discussed that the local structure of these graphs near a vertex is a deregular tree, and in fact every deregular graph has a covering space which is a deregular tree. Now how fast does a random walk move on a deregular tree? We said that, so let's, okay, maybe this will be enough. So let's look at the three regular tree. Okay, and look at the particle. This is the root here. Look at the particle somewhere, except at the root, it will only spend a small time at the root. So here is some other vertex, not the root. So at this vertex, with probability 1/3, the particle will move closer to the root, and with probability 2/3, it will move away from the root. So the drift, the growth in the expected distance will be 1/3 in every step. So that's why, so if we look at on the regular tree, the distance from the root will indeed grow like t over 3 at time t. Now, in order to mix in this graph, we have to be able to reach most vertices, and we said already that the diameter is at least log base d minus 1 of n, but if you look at a smaller distance, then only a small proportion of the vertices will be there. So the distance from the root, in order to mix, the distance of the root has to reach this log d minus 1 n. And then, but the speed is 1/3 in the 3 regular case, and in general the same argument says the speed is d minus 2 over d. Because with probability 1 over d, the particle gets closer to the root. With probability d minus 1 over d, it gets further. When we subtract, we get d minus 2 over d. So this means that we get the inverse of that is the time where we have a chance to reach the ball of radius log d minus 1. And before that time, if we will be confined to a really small set, those that are closer to the starting point. So that's an obvious lower bound for mixing time, not just in these graphs, but in any regular graph. So even you don't need the local structure to be a tree, just because the tree covers the graph. You easily get this number as a lower bound. So that's the lower bound, and then the question is, when is there a corresponding upper bound? We see this for the Ramanujan graph. But there is no chance of proving this kind of bound using L2. So here is a graph of the total variation distance and the L2 distance. The L2 distance could be very high, so we truncated it 1. The point to see is that the L2 distance goes down later than the L1 distance, not at the same time. So this is an exact calculation for the graph with 12,000 vertices you saw before. So an exact calculation of the total variation distance. So you need a co-author that's adept with doing these calculations. But this is the asymptotics. So this is what I told you is the mixing time in L1. You can also define a mixing time in L2, and this will be at a different constant. Rho here is 2 root d minus 1. Anyway, the exact value here doesn't matter, but the point is the mixing time in L2 is larger by some constant factor. The constant depends on b. Then the mixing time in L1, which means if you do the very precise calculations in L2, it won't help you to prove the cutoff in L1, which is why the approach is thwarted. And then for years we were wondering, what we know about Ramanujan is spectral information. Spectral information we can use in L2. How can we use it for L1? Now, one approach is to use the non-backtracking walk. What is the non-backtracking walk? It's the same as random walk, except once it crosses an edge, it cannot cross that same edge immediately back. So after one step, it goes to any one of the other d minus 1 possibilities except the one it just came from. I'll give a formal definition later, but it's a very simple kind of Markov chain with a extra memory of 1. There is a connection of the spectrum of the non-backtracking walk to the spectrum of the ordinary walk. And when initially we thought of maybe we could use the non-backtracking walk, we thought, well, there is an equivalence between the spectra, and since we know that the direct spectral approach fails for the random walk, it should be the same for the non-backtracking walk because of this equivalence. But that was wrong. This is a graph, again, an empirical graph of exact total variation distance. Now, for the non-backtracking walk, comparing it in L1 and in L2 on this Lubotzky Phillips graph. So you see that here they are much closer than here. Now, for the asymptotic, I didn't draw a graph here because what turns out is the asymptotics are exactly the same for L1 and L2 for the non-backtracking walk. So the first order asymptotics. let me mention, since I talked about graph distances, we have an extension. So we can describe what are the graph distances for most vertices. So take a Ramanujan graph, fix a vertex x and g, and count how many y's have distance different from log d minus 1n. So this is some perturbation of lower order. And the number of these y's is little o of n. Okay? So what this means, most vertices are at distance log d minus 1n with an error of lower order. So although we don't know the diameter, if we just care about typical vertices, we do know the answer. So we prove this using the non-backtracking walk, but Peter Sarnak told me that he knows how to do this, using Chebyshev polynomials. And indeed, there is an exposition of that approach in this paper by Sardari, I mentioned. The approach to non-backtracking walks gives you some more information. So here is something that you can get from our approach, but not from the Chebyshev polynomials. Distance between directed edges. So here is one directed edges, from x to x prime, and here is another directed edge from y to y prime. Then what we know is that for almost fix any edge x prime, then for almost all other edges y prime, there is a directed path going from this to this that goes through this edge in this correct direction. So if you just know about vertices, you can get from x prime, you can get to y, but maybe the way you get to y is from y prime in this direction. And if you do, then it's very hard to turn. It might take you a long time to turn. So you don't want to do that. You want to approach a different way. But we know that if you weight log d minus 1n, you can really go through in any direction you like. Okay. I want to quickly point out that our approach works not just for Ramanujan, but also for weakly Ramanujan. So we can get the same results about mixing time and about distances for weakly Ramanujan graphs as for Ramanujan. So in particular, these apply to the random lifts I told you about. So if you take a Ramanujan graph and take a lift, a random lift, we don't know whether that can be Ramanujan, but we do know, again, the theorem of Friedman and co-authors, that this is a weakly Ramanujan graph. And hence we have the mixing time and also this kind of result on distances. In any weakly Ramanujan sequence, the number of y, so that the distance divided by log d minus 1n is far away from 1, is little o. By the way, this easily implies the upper bound I told you, the old upper bound of 2 on the diameter, because if I have two vertices x and z, I can always go through them by stopping in the middle at a typical vertex. So the distance to the typical vertex is log d minus 1n, and then just use the triangle inequality. So that explains one way to see this factor 2. We can calculate distances in other LP, and I won't write down the formulas, but the basic conclusion is that the Ramanujan graphs, if you measure distance in any LP, they mix as fast as possible for d-regular graphs. And there are exact graphs of how the distances decay, so in different LPs. I won't go into that due to time. And I want to finish with just a quick discussion of the key tool we use, these non-backtracking walks. So again, these non-backtracking walks are a Markov chain on the space of edges. You go from an edge xy to the next directed edge, but you cannot go back along the edge you just crossed. So these were used in some of these proofs of graphs being Ramanujan. And they're convenient for us because there is an easy reduction from, if you can prove L1 mixing for the non-backtracking walk, then you get L1 mixing for the simple random walk just by multiplying by a factor d over d minus 2. What is the reason? The reason is, if you look at the covering tree, what is the covering tree of a graph? Well, one construction is fix a base node and look at all non-backtracking paths from this base node. They have a natural tree structure, and that is the covering tree. And if you do a simple random walk on the covering tree, it projects to simple random walk on the graph. Now, if I run simple random walk on a tree for some time t, the resulting node will be at some distance that I can estimate. The distance will be d minus 2 over d times t. And given the distance, it will be uniform over a level that distance, just by symmetry. So in order, suppose I know that non-backtracking walk mixes on a graph. What does that mean? I mean I can take, on the covering tree, I can take a certain level L, and if I project that level to the graph, I mixed. So what this means is that for the simple random walk, I just have to run for time, which is d over d minus 2 larger, and then I will be in some random level, and these random levels, when they project them to the graph, they're all uniform, and if I average a few uniform things, it's still uniform. So I'm not giving the exact details, but if you've seen these kind of arguments, it's very simple. So if you understand L1 mixing for non-backtracking walk, you understand for simple random walk, you just have to multiply by this inverse speed. So we want to understand the non-backtracking walk. If A is the adjacency matrix, these are its eigenvalues. We are looking now at the set of directed edges. There are d times n of these directed edges, and the non-backtracking walk is just governed by this directed adjacency matrix. So B for 2 directed edges, B is 1 if D equals X. So this means that one edge follows the other, but U must not equal Y. The edges cannot reverse. So this is the relevant adjacency matrix. To get the real Markov chain we have, we just have to normalize this matrix by a factor d minus 1, because this is a capital N by capital N matrix with row sums of d minus 1. So you normalize by d minus 1, you get a stochastic matrix. Anyway, this matrix, its spectrum has been understood for a while. So it has eigenvalues. It has an eigenvalue of d minus 1 because just that's the row sums. It has some unimportant eigenvalues that are plus minus 1. Those will really not turn out to be important. And then all the important eigenvalues satisfy this equation. So for every eigenvalue lambda of the original matrix A, you write down this quadratic equation, and it has 2 solutions. Those solutions are the eigenvalues, corresponding eigenvalues of D. And let me maybe jump to the picture first. So in the Ramanujan case, what we find, well, this is what one knows, is that this non-backtracking operator B, all its eigenvalues are all the non-trivial ones, all the interesting ones, all those arising from that quadratic equation, lie on a circle of radius root d minus 1, and they come in conjugate pairs. And these 2 pictures represent that they can still have different structure. This is the LPS graph. This is the random lift. So here you have high multiplicities and kind of some gaps. Here, the gaps are very small. Now, so this was this Bass theorem tells you what is a spectrum. In order to analyze the non-backtracking walk, we had to go further. Just knowing the spectrum is not enough, because the non-backtracking operator is not self-adjoint. So it cannot be exactly diagonalized. I mean, it's not even a normal matrix. So it cannot be exactly diagonalized by unitary transformation. But it turns out it can almost be diagonalized. And this is the precise statement. So if you write its Jordan form, all the blocks are 2 by 2. So you have, so what is the Jordan form? Well, there is this eigenvalue d minus 1, and there are the plus minus 1 eigenvalues that turn out to be unimportant. But And they are all diagonal. But the interesting part is a bunch of 2 by 2 shocking statement, I can see. So the Jordan blocks are all 2 by 2. So these, on the diagonal, you have the solutions of the quadratic equation, the Bass equation. And off diagonal, you have elements that we can also write down explicitly. So in the Ramanujan case, all these off diagonal elements are exactly d minus 2. So given how simple the statement is, it's kind of amazing it wasn't observed before, because even if you numerically take a large matrix and find the Jordan form, you will see the structure. It's a very standing out. But as far as we know, it hasn't been pointed out. It's not hard to verify this, but it's crucial in our analysis. So let me say that if all the eigenvalues were distinct, then it's easy to see you would get, if all the eigenvalues of A, the adjacency matrix, were distinct, then this kind of conclusion of the 2 by 2 structure would be easy. But the trouble is that in the interesting examples, the eigenvalues of A come with very high multiplicity. And then you might worry that this, when you go to B, you will get Jordan blocks of size of this multiplicity, root n by root n, and this would kill our analysis. So it's really important that it's only a small Jordan block. Okay. Once we have small Jordan blocks, then really the behavior of the diagonal kind of dominates. So just a quick calculation, mu t is the distribution of the non-backtracking walk at time t. So it's just obtained by taking the matrix B, normalizing it by d minus 1, and running to time t. And now we're computing L2 distance. So L2 distance is very easy to calculate. Now first, make believe that the matrix actually was diagonal. So we didn't have these off-diagonal terms. Then it's very standard to do this calculation. You just get the contribution from these eigenvalues. Now, the t we're going to take is log d minus 1n plus a small correction. So with that in mind, all the plus minus 1 eigenvalues, although they are the majority, they make a negligible contribution, because this is normalized by something which is like, this turns out to be like n squared, and on the top you have something of order n. So this is negligible. So the interesting eigenvalues live up to their names. They dominate the behavior. Now, each of these, you have to take theta I to the power 2t, because we're taking the L2 norm squared. So theta I to the 2t. And you have to normalize by d minus 1 to the 2t. So the absolute value of each theta I is root d minus 1. And when you look at this ratio, it's going to give you overall 1 over d minus 1 to the t. So it's like 1 over little n. And you're summing n terms. So this will be order 1. And so just by making this constant large enough, you can make this order 1 thing be epsilon. So that's the intuition. And then to make a more exact calculation, which I won't put on the slides, you have to take into account these extra terms. So, well, we are very good at taking a number to a power t, but a 2 by 2 matrix is almost as easy to take to power t. A triangular 2 by 2 matrix is very easy to take to power t. So you can just extend this calculation and get the result, except the correction now, instead of being order 1, it is log n, but still negligible to this log n. So I guess I don't have time to show you, but there is an easy way to see how the eigenvalues of A and B are related. But I'll skip this slide and just end with one key fact that we use in the analysis, which I don't know if of any early reference, but it is in my book with Russ Lyons, which after 19 years we finally submitted to the publisher. This is Probability and Trees and Networks. By the way, this is available from Russ Lyons' page, and it will stay there. So we're not going to remove it even after the book is published. So here is this observation which we use. So take B, and this is really the last slide. Take B, which is this non-backtracking matrix I told you about. It's always invertible, that's known. And if you take, if the base graph is connected, and take the inverse and multiply by d minus 1 and add these two things. then you get a matrix C, which I can write here explicitly what it is. And it's not important, but the important thing is that C is symmetric. So, of course, A, the matrix we started out with, the adjacency matrix of the original graph, is symmetric, but it's on a smaller space. So that makes the analysis a little bit cumbersome to go from A to B, because you have to add a lot of extra eigenvalues. But B and C are on the same space, this space of directed edges, and C is symmetric. So C, we know, has a nice diagonalization with so it's unitarily diagonalizable. But because of this formula, we see again the connection between the eigenvalues of B and those of C. For any eigenvalue theta of B, then if you take theta plus B minus 1 times theta inverse, you'll get an eigenvalue of C. And if you write it out, you'll see it's the same quadratic equation we had before, kind of recurs here, but this allows better handling and is key to checking that the Jordan blocks are indeed 2 by 2. Thanks for your attention.
Thank you very much for asking talk. Matches the interest of many people here. Probabilist and graph theories. So does it impose some kind of random walk like thing?
Yeah. I guess so, but I don't know what it is. Ah, yes. Yes, and it does so the of course when you do every second you will be concentrated on one of the color classes. And it will be mixing on that color class in the same time, d over d minus 2 times log. Yes. And if you want another way to state it, in the bipartite case, it's enough to add one lazy move. So make the first move lazy with probability half you stay in place, probability half you move. After that, you just continue with the random walk, and then this will mix in the same time, d over d minus 2 times log of n. So that's yes. Uh-huh. Yes. I don't know. Yeah, it's so. I mean, the random lift. So since we start with the Ramanujan graph, which is so small, then this graph shares some features just with the random d-regular graph. So, it's like correlation doesn't imply causation. I think both things are implied by the randomness, but having the small diameter and having the smoothness of the spherical measure, whether they are more directly linked beyond the random case, I doubt, but I don't know.
Your last answer is strange for me in the following sense. One lazy move can be that I don't go anywhere, and then in every second, so something, most probably I misunderstand something.
So that's fine. But when I talk about mixing, I look at the distribution of time t, and that combines these possibilities.
And this is a union of 1/2 times I don't move and 1/2 times
that's
I
right.
move. And
So it's but these two parts of the graph they have equal.
If I move, then everything that I want is okay. But if I don't move,
No,
then
I
it's
mean-
not okay.
No.
With one, so what I'm asking, you answered basically my question, but I'm saying that just one lazy move,
No.
lazy move, it doesn't seem to be.
Yeah, no. One lazy move is enough. Look, if we just look at an even number of steps, if we have t which is even, and we will just run the simple random walking linear steps, we will be uniform for the right time.
Yes.
Will be uniformly distributed
Every second.
over the one half of the graph.
Yes.
If we do a odd number of moves of the same
You're
order,
right, yeah, okay, yeah.
I'm just averaging
There was
the
another
uniform
more
measures.
important question of mine. This was just, I was just sleepy or whatever. The more important thing is that, so Nati quite often spoke about these liftings. This
Yes.
is one of his favorite things.
Yes.
But this was the first time when I really felt that
We
this.
should not record over